Today on Macaulay Math, rational functions and asymptotes. Intro. Okay, good day. I'm Professor Macaulay. This is Math 150, Pre-Calculus,
Lesson 9
on rational functions and asymptotes. Our goals for today: we're going to find the domains of rational functions. We're going to find horizontal and vertical asymptotes of rational functions. We're going to use rational functions to model and solve problems, and then we're going to solve rational inequalities. Rational functions produce interesting graphs because it's the first time most students encounter asymptotes. And while graphing rational functions will be discussed in the next lesson, this lesson teaches how to find these asymptotes and the implication that an asymptote has when applying them to problems in the world outside of our wonderful world of mathematics.
Let's start with the definition. A rational function is a function that is a ratio of two polynomial functions. So a rational function is something new. Up until now, we've been talking about polynomial functions. Linear functions, quadratic functions are both examples of polynomial functions. A rational function is just a ratio or a fraction made from two polynomial functions. As a quick example, I'm going to show the rational function y equals 1 over x. And these are 1 and x are two simple polynomial expressions. And we're going to start talking about asymptotes. So if I go to Desmos and we look at this graph, f of x is equal to 1 over x, we see that we have a significantly different shape than what we've been looking at graphs from before. You'll notice that there is this big disruption here around the origin. That is due to the fact that you cannot divide by 0. And so if we made a table of values, we can plug in numbers like -2, -1, 1, and 2. But when we get to 0, we get an undefined. You cannot plug in 0 because you cannot divide by 0. So when you get an undefined, you have the possibility of having what we're going to call an asymptote. In this case, it is a vertical asymptote. So let's try and define those. First definition, the line x is equal to a, and anything x is equal to just a constant is going to be a vertical line. The line x equals a is a vertical asymptote of the graph of f when f of x goes to positive infinity or f of x goes to negative infinity as x gets closer to a. And so this little arrow here implies that it's getting closer and closer to whatever value, or in this case for infinity, the concept. So as x gets close to a, the function either goes to positive infinity or to negative infinity. Now I have a Desmos demonstration to show what I mean by that. So we're trying to demonstrate a vertical asymptote. So I have this graph here, and I'm going to put in what is going to be my vertical asymptote. Now, the line x is equal to 1 is going to be this vertical asymptote for me. And we want to know what happens to the graph as the x values get closer and closer to this 1. So if I'm coming in from the left-hand side following this red curve, as x gets closer and closer to 1, this function gets closer and closer and tends to look very much like this vertical line. And then as we come in from the right-hand side and go, the function is going to get closer and closer to that vertical asymptote. If we were to pull out, it's going to look more and more like this vertical asymptote as we get closer and closer to that. The line y is equal to b, and remember, y equal to b is going to be a horizontal line. The line y equals to b is a horizontal asymptote of the graph of f when f of x goes to be as x goes to infinity or as x goes to negative infinity. So as the x values get infinitely large, either positively or negatively, the function tends to go to a single value. And again, we're thinking of an asymptote as a boundary line. So let's go back to Desmos. And we want to talk about a horizontal asymptote. So I'm going to say that this blue line is my horizontal asymptote, and my red curve is the function. So as the function tends to go towards infinity, so as I plug in x values that get bigger and bigger and bigger and bigger, this function is going to tend to look like the horizontal asymptote. And we can see as I get closer and closer to positive infinity, that function is going to look more and more like the vertical asymptote. Similarly, as I go towards negative infinity, the function is going to also look more and more like that vertical asymptote. Vertical asymptotes, any non-reducible factor of the denominator that produces a division by zero will produce a vertical asymptote. We will show examples of reducible and non-reducible zeros in a moment, but a reducible factor of the denominator will not produce a vertical asymptote, but instead it will produce a hole in the graph. And unfortunately, that is one of the weaknesses of Desmos. It will not be shown on the graphing calculator. When you are asked to find the domain of a rational function, the rules for finding domain of a rational equation are the same as those for finding a polynomial equation. You are going to start with all real numbers, and any divisions by zero must be removed by the domain. We've been talking about divisions by zero, so when we're talking about rational function, our domains are going to be limited anywhere there's a division by zero. Any square roots or logarithms of a negative number, there will be no square roots or logarithms in these types. And then any value that doesn't make sense in the context of the problem, we will have some application problems. There are rules for finding horizontal asymptotes as well. They're a little bit more simple than finding the vertical ones. All you do is compare the degree of the numerator and the denominator, and there are three different options. If the degree of the numerator is greater than the degree of the denominator, then there is no horizontal asymptote. If the degree of the numerator is equal to the degree of the denominator, then the horizontal asymptote is the ratio of the two leading coefficients. And if the degree of the numerator is less than the degree of the denominator, then the horizontal asymptote is zero. I will refer back to this page when we get to examples finding horizontal asymptotes. Our first example, given a function f of x is equal to 4x over x squared minus 1. Find the domain of the function, find the vertical asymptotes, and then find the horizontal asymptotes. Alright, so let's break this down. Let's start with part A. Find the domain of the function. Well, the first thing that I'm going to do is I'm going to take the original function and I'm going to factor the numerator and the denominator. And in this particular instance, there's nothing really I can do with the numerator, but the denominator is a difference of squares. So I can go 4x on the top, and then on the bottom I'll have x minus 1 and then x plus 1. And so here there are two divisions by zero. And so here we're going to say that our domain is going to be all values of x such that x is not equal to positive 1 or negative 1. Now if you wanted to use interval notation, that's going to be a little bit more involved. You could also say from negative infinity to negative 1 unioned with negative 1 to 1 unioned with 1 to positive infinity. Or you could write it out. Either way, it's fine. Find the vertical asymptotes, and if we go back to talk about vertical asymptotes, Any non-reducible factor of the denominator that produces a division by 0 will produce a vertical asymptote. So we want to talk about this non-reducible. So when I look at this function that I have right here, I have two factors in the denominator. I have x minus 1 and I have x plus 1. There are no equivalent factors in the numerator for each of these two factors. So both x equal to 1 and x equal to negative 1 is going to produce a vertical asymptote. Part C asks us to find the horizontal asymptotes. Well, if we go back to this list here, we are going to be comparing the degree of the numerator to the degree of the denominator. In this particular instance, the degree of the numerator is just 1 and the degree of the denominator is 2. Therefore, the degree of the denominator is greater than the degree of the numerator, so our horizontal asymptote is just going to be y equal to 0. Now if we go to Desmos and plug this in, you will see that all of these values are true. And so here I have the function plugged in, 4x over x squared minus 1. If I type in x is equal to 1, I have a vertical asymptote, and it does look like they have that vertical asymptote. If I type in x is equal to negative 1, I have another vertical asymptote, and the function does appear to show a vertical asymptote there. And then finally, if I go y is equal to 0, I get a horizontal asymptote, and clearly the function looks like that now. If I zoom out, my red function is going to look more and more like the vertical and horizontal asymptotes, and you can see that fairly quickly. Next example, find all the given asymptotes and then use graphing calculator to verify your answer. All right, so I'm going to start with this function here, and I am going to factor the numerator and the denominator. So I'll start with that f of x is equal to x squared minus 4x over x squared minus 4. In the numerator, I'm going to have to do a GCF. So I'll have x times x minus 4. And then in the denominator, I again have a difference of squares. So I'll have x minus 2 and then x plus 2. And you'll notice none of the factors in the denominator will cancel out with a factor in the numerator. So there are no irreducible divisions by 0. And so in part A, when I talk about my vertical asymptotes, I am going to have one at x equals 2 and at x equals negative 2, because that's where I'm going to get divisions by 0. My horizontal asymptote I will again go back to that list of 3 things and compare my degrees. If the degree of the numerator is equal to the degree of the denominator, then the horizontal asymptote is the ratio of the two leading coefficients. So if I go back to this example, my degree of the numerator is 2, the degree of the denominator is 2, so my horizontal asymptote is going to be the ratio of the leading coefficients. In this case, I have a 1 and a 1. 1 over 1 is 1, so my horizontal asymptote is going to be y is equal to 1. And again, if we go to Desmos, we can see that. Here we can see I have entered x squared minus 4x all over x squared minus 4. If we type in the vertical asymptotes first, x equals to negative 2, x equals to positive 2, and y equals to 1, we can in fact see that all of our asymptotes do look like they are going to match up. Next example, Here we have something that's a little bit more involved. Again, we're going to start by factoring this. Now we've spent some time factoring quadratics, so we see this function is a little bit more complex than the last one. For the sake of brevity, I am just going to show the factorization. If you need me to review how I get these factors, let me know in class and I can go through it. But the factorization of this thing will be f of x is equal to 3 plus x times 1 minus 5x, and in the denominator we'll have 3 plus x and 1 plus 2x. And this is the first instance in which we have a reducible factor. Notice I have 3 plus x in the numerator and I have 3 plus x in the denominator. So these two things tend to cancel out, but that doesn't mean that the division by 0 goes away. And I will show that in Desmos. But it does mean that instead of a vertical asymptote, what we will have is a hole. So when you look at part B, it says find the holes of the graph. This thing is going to have one. So in part A, when I say that I'm going to have vertical asymptote, well, this 1 plus 2x does not reduce with anything in the numerator. So I need a vertical asymptote for that 0. Now, if you can't do it in your head, that's okay. We just need to know what makes the factor equal to 0. So if I go 1 plus 2x is equal to 0, I subtract 1, I get 2x is equal to negative 1. I divide by 2, I get x is equal to negative 1/2. That is my vertical asymptote. Negative, make that look a little bit better. My horizontal asymptote and again, we have an instance where the degree of the numerator is 2 and the degree of the denominator is 2. So the ratio of the leading coefficients will be negative 5 over 2. So my horizontal asymptote will be y equals to negative 5 over 2. In this case, we do have a hole, and that is going to be at x equals, and again we have this reducible factor both in the numerator and the denominator, so it's going to cause a hole. It's still going to be undefined there, but at x equals negative 3 we'll have a hole, and we're going to verify that using graphing calculator. So let's plug this thing back into Desmos and show that all of the things that we found are true. And so here we have our graph, and we said that we had a vertical asymptote at x equals negative 1/2. That looks right. And a horizontal asymptote at y is equal to negative 5 over 2. And we see that that's true. Now the last thing I want to talk about is the hole. And we said that the hole was at negative 3. So I'm going to put my dot on the function, and I'm going to get closer and closer to negative 3. And when we get to exactly negative 3, you'll see that there's a hole there. And it only shows the hole if I have my cursor right on that undefined. And so it doesn't show it on the graph. So you've got to be careful with the holes in the graph. Next example, given h of x is equal to x squared minus 11 over x to the third plus 8. It says find the zeros of the function, use a graphing calculator to verify the zero of any function, regardless if it's a polynomial or a rational function, is any value for x that causes the function to be equal to 0. Now for a rational function, or any fraction for that matter, to be 0, the numerator has to be 0. So if I set x squared minus 11 equal to 0 and solve that, so I'll add 11 to both sides, and I'll take the square root, and another reminder that when you take the square root, you add your plus or minus the square root of 11. And that's not going to reduce because 11 is a prime number. And so these are my potential zeros. Now the only possible problem is that if square root of 11 or square root of negative 11 is a 0 of this thing, now x to the third plus 8 is a sum of cubes. And you probably have not seen a sum of cubes since Algebra 2. And so if I have a to the third plus b to the third, there is a factoring method for that. It is a plus b times a squared minus ab plus b squared. And this second quadratic is not reducible over the real numbers. So here I can say that the factorization of this, if x to the third is a to the third, then a is just going to be x. And if 8 is b to the third, then b is just going to be 2. And then I'll have x squared plus 2b plus 2 squared is 4. And so x plus 2 will be in the denominator. So the factorization of this thing would look like this. It would look like x minus square root of 11, and then x plus square root of 11 all over x plus 2 times x squared minus 2x plus 4. And again, none of the factors in the denominator cancel with ones in the numerator. So my zeros will be x is equal to plus or minus the square root of 11. And if we go to Desmos and type the function in, here's our function, x squared minus 11 over x to the third plus 8. We do get this kind of funky looking graph here. But we do in fact find that the zeros are at plus and minus square root of 11. We can just type in and we can see real fast that they do in fact match up. This 7 here, that will round up. All right, next example. The sales S in thousands of units for a tablet computer during the nth week after the tablet is released are given by S is equal to 150n over n squared plus 100. Use a graphing utility to graph the sales of the function. Find the sales in week 5, 10, and 20. And according to this model, will the sales ever drop to 0 units? And let's explain that. Alright, so since they are telling us to use a graphing utility right off the bat, let's go to Desmos and type that in. And so here, I've typed into our standard window, f of x is equal to 150x over x squared plus 100. And we really don't see a whole lot of this graph. And we also know that they want to know the sales in week 5, 10, and 20. And so I see 5 and 10 on the graph, even though I don't really see it. So let's open our window a little bit more to see some more stuff about the graph. And so the first thing I'm going to do is I'm going to open up the x-axis and 1, 0, that make it 200 here. And then for the y's, we don't have to make it much bigger. It doesn't look. Let's go with 15. And then we get the, okay, so we have this graph. So remember what we're selling. We're selling brand new tablets, and the X values are weeks. So when it comes out, there's no sales because we haven't sold one yet. And then it's something new, so a bunch of sales right away. And then it starts to level off to something that's going to be a little bit smaller sales per week. Now, if I want to find the sales, and again, it's in thousands of units, for weeks 5, 10, and 20, I would plug 5, 10, and 20 in there. But since we have Desmos, if I have to plug a number into the function more than twice, I'm going to use a table. So let's make a table. Call this f of x1. And let's go 5, and then 10, and then 20. So on weeks 5, they sell 6,000 units, and that seems to be right there. And then at week 10, it looks like the peak where they're selling 7,500 units. And then on week 20, it looks like they're used selling 6,000 units again, and it's going to go down forever. Part B, week 5, week 10, and week 20. Here we sold 6,000 units, and then on week 10, 7.5 thousand units. And then in week 20, we sold 6,000 units again. So part C, it says, according to the model, will the sales ever drop to 0 units? Let's explain that. All right, now according to the model, okay, let's talk about real world versus the model. According to the model, I have a horizontal asymptote at S equals to 0. And I know that because the degree of the numerator is 1 and the degree of the denominator is 2. So this thing is going to shrink to 0, but since it's an asymptote, it's never actually going to shrink to 0. But in the real world, they're eventually going to stop selling tablets once a new one comes out. So, according to the example, no. So according to the model, there is a horizontal asymptote at S equals to 0. So there will be no point where it drops to 0 units. But in the real world, the model will eventually be discontinued. All right. Finally, solving rational inequalities. Solving rational inequalities will be very similar to solving polynomial inequalities. We'll write the inequality as a single fraction on one side of the inequality symbol. We will find the zeros of the numerator and the non-reducible zeros of the denominator. These are your critical values, the only places where the inequality can change from positive to negative. And then we'll use a sign chart to determine where the rational expression is either positive or negative. And then we will determine the regions that make the inequality true. So let's look at an example. It says solve this inequality, and good news for us, the inequality is already written as a single fraction, and it's on one side of the inequality symbol. So we have something that's less than 0. And so I'm going to find all of the zeros. What makes x minus 1 equal to 0? Well, positive 1 does. So my first 0 is going to be x is equal to 1. And then in the denominator, if I factor the denominator, x minus 1 on the top, and then this is a difference of squares again, so x minus 3, x plus 3, and I have divisions by 0 at x equals 3 and x equals negative 3, and these things are going to be our critical numbers. And so I'm going to make a number line here. I'm going to put in those critical numbers. Negative 3 of 1, and then we'll have positive 3. And this function here wants to know the x values where the expression is less than 0, or what values of x makes this function negative. Anything less than 0 has to be negative. So I'm going to pick values in each of these intervals. This first interval here, we'll pick negative 10. If I plug in negative 10, negative 10 minus 1 is negative. Negative 10 squared is 100 minus 9 is positive. So I get a negative divided by a positive. Therefore, this result is negative. if I pick a number between -3 and 1. So let's say I pick 0. 0 would be easy because it's been in there. I get -1 over -9. That is a positive. Let's say I pick 2. 2 minus 1 is positive. 2 squared is 4 minus 9 is negative. Positive divided by a negative is a negative. And then in this last interval, let's say I pick 10 again. 10 minus 1 is positive. 10 squared minus 9 is positive. This is positive. And so again, the question asks, where is this function less than 0? And we see here that it's less than 0 here and here. So our final answer will be from -infinity to -3, unioned with 1 to 3. And we can check that looking in decimals. And again, we want to know where this function is less than 0. So we'll type in the function. And here I have the function, x minus 1 over x squared minus 9. And we can see here at from -infinity all the way up until we get to 3. From -infinity until we get to 3, it's less than 0. And then from 1 until we get to +3, it's less than 0. Everywhere else, the function is above the x-axis, therefore it is positive, and we feel very confident about our final answer right here. Well, that's all I have for today, folks. So, the Star Wars fun fact of the day: Chewbacca was inspired by George Lucas' Alaskan Malamute named Indiana. On a side note, the dog also inspired Mr. Lucas' other famous character, Indiana Jones. Well, that's all I got for today, folks. Have a good day. Bye.